Okay, so I guess we can start. So thank you very much for inviting me to the Aggregation Institute for this talk, for the Junior Researchers talk. Today I'll be talking about self-reinforcement and how that plays into superdiffusion and subdiffusion for applied purposes. So my name is Daniel Khan. I was previously at the University of Manchester working with Professor Sergei Fedotov, and now I'm based in Cambridge, joined at the MRC Laboratory of Molecular Biology and the University of Cambridge. Okay, so today I'm just going to basically present to you about a new persistent random walk model that can actually generate superdiffusion with exponential runs. And so this is something new that has played a huge role in modeling endosomes inside cells. And then I will extend this model to incorporate resting states in the random walk. And then I'll also talk to you a bit about variable or fractional diffusion, which occurs when the media is like heterogeneous and the subdiffusion going on in there. So this work is all based on a series of papers. These 5 papers, if you're interested. So what's the biological motivation? Well, in 2015, about when I started my PhD, or 2 years earlier, this group in Korea found that endosomes were actually moving with self-reinforcing directionality. Now, what does that mean? That actually means that these endosomes were moving along microtubules. So the first picture you see there in green are little tubulin bundles inside cells. Each blue dot is the nucleus of the cell, and the red dots that you see are membrane-bound vesicles that move along these tubules. If you go and measure the motion of those red particles, which is shown as, the blue round balls in the diagram, they move along the green cables that are shown in the first picture, and they pause at certain times, and then they run very, very fast, ballistically at other times. And what this group found was that actually the distance that these endosomes travel between the pauses were exponentially distributed, and yet somehow these particles, the ensemble behavior, were displaying superdiffusive characteristics. That basically means that the mean square displacement is proportional to time to the power of between 1 and 2. Okay. And in normal random walk theory, when something has exponentially distributed runs or exponentially distributed times, usually we'd expect central limit theorem and everything to be diffusive. Gaussian distribution, you get diffusion with mean square displacement proportional directly to time. Okay. So in order to model this, we began with a persistent random walk model, a very simple model, where you see in equation 1, lambda brackets 1 minus q plus minus. And that can be regarded as your conditional switching rate probability. And that q plus or q minus is actually what determines the self-reinforcing directionality coefficient, which transforms your exponentially distributed times so that your particle now can essentially run immediately after a previous run in the same direction. Okay? Usually, models like the ones you saw here with finite velocity, which is first term, are usually alternating models. But if we introduce q plus, q minus here, very simply we can get a model that actually goes in the same direction multiple times before switching directions. And that's exactly what you see here. And this was the rationale behind creating such a model, because this is how endosomes were walking. So you have multiple successions of runs in the same direction, and then a switching direction. And these multiple runs altogether are what constitutes a flight. So individual runs self-organize into a long flight. And in order to obtain the superdiffusion that we saw with these endosomes, we required a very, very specific type of conditional transition probabilities, which is written out in equation 2 here. So q plus and minus is equal to some parameter, w, and that will be known as kind of the self-reinforcement parameter. And then you have the time that the particle has traveled in the positive direction versus the time that the particle has traveled in the negative direction, t plus and t minus, divided by the total time. In other words, what does that mean? The particle is essentially moving along, picking out randomly distributed times from the exponential distribution we bring like that, and then stopping, and basically, depending on how long it's traveled in the positive direction, and also the negative direction, that governs its choice to either continue in the positive direction or switch direction and go in the negative direction. Okay. Now, how can we incorporate the equation 2 into our main master equation, which is in equation 1, and essentially obtain a PDE that governs all of this? And you can do this easily by saying, total time is equal to the sum of the times, and the position is actually the difference of these t plus t minus times spent traveling forwards and backwards. And you end up with a very nice looking formula, number 3. And from now on, we'll talk about 2w minus 1 as alpha in the self-reinforcement parameter. And you can see this is going to create a very, very strange advection term when we formulate the PDE, which is essentially here in equation 5. So when you take equation 4 and you apply the sum of probabilities and then the flux, you join them together, you end up with equation 5. And this essentially gives you the term, the last term, equation 5. And it turns out that if you actually try to work out the first and second moments for these random walks, you end up with a very funny result. Well, you end up first of all with an ODE, second order ODE for the first and second moments. And when you solve these, you actually end up, we can actually solve this exactly, which takes a bit of time. And you end up with the hyperconfluent hypergeometric, the Kummer-confluent hypergeometric function. And in the asymptote of time going to infinity, you see that the first moment is actually proportional to t to the power alpha, where alpha is that self-reinforcement directionality parameter that you saw. And the second term, the second moment is diffusive for a very specific value range of alpha, which actually corresponds to your self-reinforcing directionality proponent of 0.75, so 3/4 and less. But if W is basically greater than 0.75, you end up with superdiffusion, e to the power of 2 alpha. Alpha is between half and 1, so the exponent is greater than 1 and less than 2. And what does that mean? Basically, we can now, from this model and from the way that we've modeled self-reinforcing directionality, we can actually achieve superdiffusion from a series of exponentially distributed flights, of exponentially distributed runs. And we've also found the critical value of W, the amount, the propensity of that particle to essentially engage in measuring its past behavior and making the future decision. Based on that value being greater than 3/4, it actually generates superdiffusion. And if it's less than 3/4, it does not generate. So then we're able to obtain exact solutions for the PDF, for the diffusive regime, and also perform multi-color simulations for when for both superdiffusive regimes. And as you can see, what generates the superdiffusion in the ensemble mean squared displacement is actually the fact that the particles have a bimodal distribution and are moving away kind of almost ballistically, but with a bit of diffusion along the groups in the bimodal range. So then next, we can actually calculate what are the flight lengths based on the sum of exponential flights. And this is very important because Levy walks usually are defined by the fact that they have power law distributed flights in CTLV theory. Well, so if we calculate the conditional transition rate, so this transition rate would be given that I switch directions at x star, at position x star and time t star, what is the rate at which I then stay in that state of positive or negative velocity? Okay. And from this, you can also obtain, so that's the first equation here. And from this, you can actually obtain the conditional survival probability. In other words, given that I've switched directions just at position x star and at time t star, what's the probability that I survive up to time tau? Okay. Actually, something very, very beautiful, because for many, many years in biological research, what the applied mathematicians have had to do is actually temper artificially some kind of power law distribution they model. And yet from this persistent random walk model, we see that the tempering arises naturally out of the fact that we have such a history-dependent random walk. So this lambda 1 minus w, which is actually coming out of that the half term that you saw before here. Yeah, this term actually generates a tempering, and this term generates your power 1z. And what this means is now this model has even more an even more advantageous attribute, that the tempering of the distribution of particle runs arises naturally out of the fact that the particle is actually beginning with an equal probability to turn left or right, or positive or negative, and then eventually, due to its history of making decisions at certain points, you end up with a parallel. So then we fitted this to experiments, and for reasonable parameters, of course, this is not finished work, but for reasonable parameters, we can actually reproduce the distribution that you see in the experimental data from this paper that originally introduced the concept of self-reinforcing directionality. Now what we can say is we have a master equation solution to all the moments that actually match this theory that was proposed in this Nature paper. The next step, clearly, because if you remember back, the endosomes were not just running and switching directions or going in the same direction, they were also resting. We can introduce rest states in a very simple manner, like equation 12, where now instead of having the transitions from positive to negative, depending on your past history, now every positive and negative run, at the end of that run, you now go into a rest state. And the rest state now governs the conditional transitions. So now the rest state is actually the part that has the self-reinforcement with when you see R plus, R minus, and R naught. And of course, those probabilities all sum to 1. If we choose, and in a very similar vein as before, we can define R plus and R minus like so, with some kind of proportional weight, multiplying the amount of time that I've traveled in the positive direction with some proportional weight, multiplying the amount of time I've traveled in the negative direction, and then now also including a weight, multiplying the time that I've been at rest. If we then, because it doesn't really make sense to allow the decision to rest, basically self-reinforce, we now choose, we don't allow that. We don't allow T naught to dominate in the dynamics. And we now try to formulate a symmetric transition, two symmetric conditional transition probabilities, R plus and R minus. And we end up with what you see in equation 14. And I hope you can see that there's a striking similarity between that and also the conditional transition probabilities that we used before. And now we can define alpha naught as W1 minus W2. And that takes different values, but this is still the same self-reinforcement parameter. Then you can actually formulate this master equation again with self-reinforcing directionality and also including rest. And what you see is very interesting because you have basically a convolution with an exponential, so you have kind of an extra complication when you try to calculate the moments or the distribution. So then you can take that equation, that master equation that you just saw, and find this equation for the second moment. And unfortunately, I wasn't able to solve this equation directly analytically, but we consider the long time limit, and you end up with equation 9, taking the class space and then allowing S to go to 0. And the solution that you obtain is in the class space is 20, and you can see that actually when you transform this back, we can actually still get superdiffusion again. So this was something, a novel result, because usually when you introduce rests, you end up destroying the subdiffusion, the superdiffusion, and now we can see that actually with self-reinforcing directionality, you can increase that, you can maintain superdiffusion even though you're introducing rests. And this is all still with exponentially distributed runs and rest times. So then we can actually work out when does the random walk generate superdiffusion and diffusion. And it all depends on the rate at which the exponential rate at which the particle either runs or rests. So lambda over eta. That's critical parameter here. And you can see that for various for values of alpha naught being very close to 2 over 3, you actually get a huge area where you can generate superdiffusion. And this was previously not really thought of. And here it's just like a Monte Carlo simulation of the variance of the particle positions, demonstrating that we can actually obtain superdiffusion as we increase the rate at which the particle leaves the rest state. So intuitively it makes sense, right? The shorter amount of time that you spend in the rest state, the more superdiffusion you experience. Actually, as eta approaches infinity, you're going to actually revert back to the case when you didn't have rests. So then, in keeping with the fractional diffusion program, what we can do is we can introduce mid-tag left-flow distributed rests. So what does this mean? This is basically your particle moving in the positive direction or the negative direction with exponentially distributed times, and then resting. But now, instead of resting with exponentially distributed times governed by eta in equation 23, you actually are resting for mid-tag left-flow distributed times, and this can be just approximated to power laws. And in doing so, we actually introduce the Riemann-Liouville derivative here. And you can see the structure of the equations are actually almost exact. So that's before. And in a similar vein as before, you take the conditional transition probabilities formulated in a symmetric way so that T0, the time that you spend at rest, does not contribute towards the dynamics at all. And what you find is that you can actually obtain a kind of a semi-telegrapher's equation, but with now the Riemann-Liouville derivative inside the advection. And when I first tried to find solutions for this kind of equation, what I did was I performed Monte Carlo simulations. And at first I thought, oh my gosh, we found superdiffusion. You know, is that even possible? If we introduce a power law resting time, is it possible to obtain superdiffusion again? Does anyone have an intuition if they can or not? Okay, so just coming from like 20 years of history of reading these papers, it's never ever been even suggested that superdiffusion can be achieved when you introduce basically mid-tag left-flow distributed rest times in certain states. And so I was almost 100% sure this Monte Carlo simulation was incorrect. And if we actually do the calculations for the asymptotic solutions, going from the master equation, we take again the Laplace space and we let S go to 0, then you end up obviously proving that actually in the asymptotic limit, where beta, so beta here is the parameter that you see in the Riemann-Liouville derivative, and that's between 0 and 1. And because this is between 0 and 1 here, the exponent, this can only be subdifused in the model. And so, of course, what we saw in the simulation is actually only a transient superdiffusion. And nonetheless, this is quite interesting because it's saying that you can actually achieve superdiffusion at very small times, but everything eventually becomes subdiffusive and basically just becomes stationary almost once you hit bond times. And you can see the bending as you increase your beta. So beta going to 1 is closer to diffusion. And you can see that as you get closer and closer to diffusion, the slower your approach to subdiffusion. This is the second. And of course, if you simulate this for a very, very long time, you end up seeing that everything reverts back to subdiffusion. So in a sense, this was quite an anticlimax, if you will. Because I thought first, superdiffusion out of fractional derivatives, that's not possible. So then next, what we did was we went to model organelles that are actually subdiffusive for most of the time. In other words, they're not transported along these wires, but actually they just float freely in space inside the cell. And it's very well known by a study published in 2008, and also other studies following that, that lysosomes move predominantly subdiffusive. They do not engage with a large amount of motor protein mediated transport. And you can see that this subdiffusion actually creates an accumulation of lysosomes. Each green dot would be one of those particles near the cell's center, which is located near the pictures that you're seeing here with the blue, that's also the nucleus of cells. So there's two in both pictures. The green dots are the lysosomes. The red dot in the right picture is Golgi. So then I went and developed a model that was using a variable order fractional diffusion equation. So in this case, imagine if mu was here in that exponent and also in the diffusion coefficient. If mu was not dependent on space, so x, this is one dimensional. And if mu was just constant, that would be the ordinary fractional diffusion equation. But once you actually introduce a variable order fractional diffusion equation, you end up with properties that you would not see otherwise. And that, in essence, is actually aggregation. So we see an aggregation when we introduce this. And basically, what we're going to do is we're going to make mu x change monotonically so that at x equals 0, you have the lowest value of mu, and at x equals 1, you have the highest value. And you'll be able to see what effects this has. Just for intuition, this random walk describes basically you have a long line of states, and you're jumping between these states with some power law distributed waiting times based on mu, where mu is that exponent. So we formulate the fractional diffusion equation with a flux, and if we look at the flux and we actually calculate it, you can see that from the derivative inside the Riemann-Liouville derivative, inside the Riemann-Liouville derivative. So taking the derivative with respect to x, you actually end up with, when you do that for this term, using simple chain product rule, you end up with this funny operator, which is, I hope you can see, it's going to depend on the logarithm of time. So yeah, we end up with a modified Riemann-Liouville operator, and that's very funny because we've never actually really seen the logarithm of time pop out from deriving such an equation. And then furthermore, from this, you can see that in the long time limit, as time approaches infinity, that logarithm begins to dominate, and any other advection caused by a gradient or an imbalance between kind of forces here in the diffusion coefficient is actually going to be dominated. So in the end, that's all that you'll have left, this funny logarithmic operator that you see. We can actually solve this. We can actually solve the original variable order fractional diffusion equation for long times, and we end up with, again, a very funny looking asymptotic representation of the solution. If we then go and perform Monte Carlo simulations, so you start off with a finite number of states between 0 and 1, x equals 0 and 1, and these particles are jumping between these states with some value of power law distributed at random times with the exponent depending on mu, which is actually different for each of the boxes. Okay. And what you see is, you actually see this aggregation. So remember, mu is the lowest value at 0, and it's the highest value at 1, x equals 1. And you see this aggregation of particles towards 0, even though we haven't actually introduced any kind of advection term. We've not actually introduced any force. This was a very funny result, very peculiar result, but intuitively, when you think about it, it makes sense, because imagine you're jumping between states, between consecutive states, and the time that you occupy each state is actually drawn from different probability distributions, probability densities. And the one at 0 has a much, much fatter tail at infinity. Right? Then it makes sense that everything gets trapped at x equals 0. then we actually went to show that even in the presence of some kind of advection, so we can introduce, so the derivation that you saw before was due to the fractional diffusion equation. Now we can actually extend this to the fractional Fokker-Planck equation. And if you do this, you can actually see that, remember that from the fractional diffusion equation term, we have that finite logarithmic operator, modified root integral derivative popping out, and that's still in here. But then in the fractional Fokker-Planck equation case, you actually have some kind of velocity advection. And you'll also see that actually as time approaches infinity, the finite logarithmic term that you saw in the previous case still dominates, because advection does not change it, it's not increase. And this is exactly what you see here. You end up with almost exactly the same solution, and yet this time I've actually even started the particles, everything in the upper half of the domain. And the inset figure actually shows you what the distribution of particles should have been like if we just followed a normal Fokker-Planck equation with some kind of velocity drift that's covered by that equation there. So not only does it create accumulation of particles at the position with the lowest normalist exponent, fractional exponent, it actually destroys any kind of advection that can be caused. And obviously this is very, very, very pertinent to cell dynamics, to intracellular dynamics, because what we do see is we actually see lysosomes distributed in such a pattern. And even with active transport, pushing these particles ballistically away from the center, which is it, we actually see that the distribution of kind of this stable accumulation at the center of the nucleus or the center of the cell is maintained exactly the same. And one of the key questions is, I guess, pushing forward is to actually verify this. And the times there, these are in seconds. So they're quite reasonable. It's not like 10,000 pieces or something. It's more like 3 hours. If we then go and directly measure for each lysosome how they're moving, we actually see that based on a normalized distance away from the cell center, we have a variation of an almost exponent that's increasing, monotonically increasing as you get further and further out to the periphery. So x equals 1 here would be at the very edge of the cell, and x equals 0 is at the very center. So what are the main takeaways? One, basically that self-reinforcing directionality can generate superdiffusion by organizing these exponential runs based on the previous history of the random. Two, that this type of reinforcement can generate superdiffusion even when you introduce rests, and be very careful because these are exponentially distributed rest types. But if we introduce, so 3, if we introduce Mittag-Leffler distributed rest times so that we incorporate a fractional derivative into the PDEs, it begins to dominate, and you can no longer generate superdiffusion, and subdiffusion is done at long times. And 4, when you have fractional diffusion with space dependencies in the anomalous exponent or the fractional exponent, it actually causes aggregation towards the state with the lowest anomalous exponent or fractional exponent. Thank you very much. So these are some of the colleagues that I'd like to thank. Sergei Fedotov, who was my PhD supervisor, Vicky Allen and Tom Way, who are my co-supervisors in biology and biophysics, and then Nikolai Korabel and Mark Johnson, 2 talented postdocs that work with me. I'd just like to thank my funding sources, University of Manchester and Wellcome Trust. Now I'm working at the Laboratory of Molecular Biology and also at Churchill College. And then thank you very much for the Young Institute for allowing me to give this talk.
Thank you very much. Any questions?
Yeah, maybe I have a stupid question. So you said that subdiffusion is something you can observe in biology.
Yes.
But now you spoke about superdiffusion.
Yes.
So superdiffusion is something more for academic reasons, or it also happens to, you can see it in biology?
Yeah, so that's a great question. Usually, the problem, that's exactly the problem you actually pointed out in the field. The problem is that superdiffusion and subdiffusion are generally treated separately in mathematics, because exactly what I said here, which is when you introduce subdiffusion into the formulas, eventually in the long-time limit, everything just becomes subdiffusive. But superdiffusion does still exist in the biology, because if you go back here, yeah, what you can see is actually these flights. You can see they're almost ballistic. So there's no way that you can model this with some kind of subdiffusive theory. It's just that in the long time limit over the ensemble, you generally just see subdiffusion. But incorporating these effects into the subdiffusive formula is what I'm trying to do, and it turns out subdiffusion just kills everything. That's one of the big problems right now. Yeah. But it might be helped because cells usually have a lifetime of 24 hours or 20 hours until you have a catastrophic event, basically, where everything dissolves, everything splits in two, and then you have to remake everything. So it might be that actually we should be studying the transient effects at short times rather than long-term asymptotic solutions.
On that matter of the transient effect, like can you measure? Can you predict or make some guess from your model on how long that takes place, and how that compares with the specifically the example you gave? Like, is the transient thing happening? Is it very short? Is it very long? Is it?
Yeah. So
like, are you expecting to actually see it? I guess is the question.
Yeah. So one of the parameters in this simulation that I guess I didn't show was that this power law distribution for runs was actually you only need about 1,000 seconds to generate this. So that's an hour, less, like 30 an hour, something like that. But then in order to generate the subdiffusive PDF that you saw here with the model, you actually need something like 3 hours. So it's order of magnitude like 10 bigger. But then obviously I can't say for sure like this is the cutoff or this is the equation of the trade-off between subdiffusion and superdiffusion. That's actually that's one of the areas that I'd like to see move forward during as future work. Yeah, finding that kind of trade-off I think can be very fruitful thing for the field. So, yeah, thank you very much.
Any further questions?
But as there's people on Zoom with questions and they want to unmute themselves, welcome to do so.
Let's thank the speaker again. Thank you very much.
You can leave it here. Yeah. We have another speaker in our J series at 1. So in the meantime, we're going to. I think it's good because we're going to church. Mostly because it's the closest one. Yeah, so you're all first welcome to join, and then we'll reconvene here at 1 for. I think our next speaker is on Zoom right now. Join lunch and yes.
I think this is